Imagine the world is finally waking up. The ice is retreating. Glaciers that buried entire landscapes under hundreds of feet of frozen water are pulling back, slowly, steadily, like a great exhale after holding its breath for tens of thousands of years. Animals are moving north into newly exposed land. Plants are reclaiming territory that hadn't seen sunlight since before anyone alive could remember. Humans, scattered in small groups across Europe, Asia, the Americas, are beginning to settle into something that almost looks like stability. The worst is over. The long freeze is ending, and then, almost overnight, it stops. The temperature drops. Not gradually, not over thousands of years the way climate is supposed to change, but fast. Shockingly, disoriently fast. In some places, average temperatures plunge by 10 degrees Celsius or more. Tundra reclaims forests. Ice advances back over land that had just been freed. Rivers that were running full and clear slow and freeze. The animals that had been moving north reverse their migration or simply disappear. And the humans who had been adapting to a warming world suddenly find themselves in something that looks a lot like the Ice Age they thought they were escaping. This happened. Around 12,800 years ago, the Earth's climate did something that should not have been possible. Something that breaks your intuition about how slowly planets change. And nobody, even today, can fully agree on why. That cold snap has a name. Scientists call it the Younger Dryas. It's named after a small Arctic flower, Dryas octopetala, whose pollen shows up in sediment layers from this period all across Europe. A flower that only grows in cold, harsh conditions, suddenly appearing in places that had been warming up for millennia. Finding that pollen in the geological record is like finding frost on a July morning. It tells you something went very wrong very quickly. The Younger Dryas lasted roughly 1,200 years, from around 12,800 years ago to about 11,500 years ago. In geological time, that is nothing. A blink, a comma in a sentence that was 100,000 years long. But in human terms, in ecological terms, in terms of what it did to every living system on Earth, 1,200 years is an eternity. Entire civilizations have risen and fallen in less time than that. Species have gone extinct. Landscapes have been permanently rewritten. And all of it triggered by a climate event that nobody saw coming, that reversed a warming trend that had been building for thousands of years, and that ended just as abruptly as it began. When scientists talk about the Younger Dryas being abrupt, they mean something specific, and it's worth sitting with that for a moment. We tend to think of climate change as something slow, something that takes millennia to fully register, and mostly that's true. But there are moments in Earth's history where the climate system crosses a threshold, tips from one state into another like a switch flipping. Ice cores drilled from Greenland, which preserve annual layers of snowfall going back hundreds of thousands of years, suggest that at the start of the Younger Dryas, temperatures in Greenland dropped by somewhere around 10 to 15 degrees Celsius in as little as a decade. A decade. 10 years. Your parents were alive 10 years ago. The climate doesn't move that fast, except when it does. And here is the mystery that has kept scientists arguing for decades. What caused it? What could possibly have been powerful enough and sudden enough to reverse the warming of an entire planet? To drag the northern hemisphere back into near-glacial conditions in the span of a human lifetime? There are suspects, several of them, and none of them have been fully proven. None of them have been fully ruled out. Some researchers point to a slowdown or collapse of the ocean's great circulation system, the massive conveyor belt of currents that moves heat around the planet. Others point to an enormous flood of fresh water, melting glaciers suddenly dumping vast quantities of cold, fresh water into the North Atlantic, disrupting that circulation, throwing the whole system into chaos. Some point to cosmic events, to the possibility that something came from above, a comet, a meteor, a swarm of fragments that hit or exploded over the Earth and triggered fires, dust, and a sudden darkening of the sky. Others look at volcanic activity, at changes in the sun, at the way land use and vegetation shifts might have fed back into the atmosphere in ways that compounded everything. None of these explanations are simple. Each one has evidence for it. Each one has evidence against it. And part of what makes the Younger Dryas one of the most fascinating and frustrating puzzles in all of climate science is that the answer might not be just one of these things. It might be several of them, interlocking, triggering each other, cascading into something larger than any single cause could produce. A perfect storm of planetary disruption. We'll walk through all of it. But first, it's worth just sitting inside the strangeness of the event itself. Because this isn't ancient history in the way we usually think about it. 12,800 years ago is not the age of the dinosaurs. It's not deep geological time. Humans were fully modern by then. They had language, tools, art. They were already living on multiple continents. The Younger Dryas happened to people. People who left no written record of what they experienced, but who left other kinds of records, in their bones, in their campsites, in the pollen and charcoal layers buried in lake sediment, in the megafauna that vanished and the ecosystems that collapsed around them. This is a story about a climate event that is old enough to feel distant but recent enough to still be shaping the world you live in today. The warmth that followed the Younger Dryas, the stable, mild climate of the last 11,500 years, is the climate in which every human civilization has ever existed. Agriculture, cities, writing, empires, all of it happened in the window of warmth that opened when the Younger Dryas finally ended. Understanding why that cold snap happened, and why it stopped, might be one of the most important questions in Earth science right now. If you're listening to this at night, trying to let your mind settle into something slow and interesting, you're in exactly the right place. That's genuinely what this channel is for. So settle in. Let the questions wash over you rather than chase you. And if you feel like it, drop a comment and tell me where in the world you're listening from and what time it is. It's one of my favourite things about this community, that on any given night, someone in Edinburgh is drifting off, someone in Melbourne is just waking up, someone in a Tokyo apartment has their headphones in at 2 a.m, and we're all in the same strange quiet together. Because the Younger Dryas is a long story and a cold one, and we're only just getting started. To understand what the Younger Dryas interrupted, you have to understand what the world looked like just before it happened. Because the cold snap didn't arrive into a stable, settled climate. It arrived into a world already mid-transformation, a world in the middle of one of the most dramatic transitions in the last 100,000 years. The Earth was thawing, and it had been thawing slowly and unevenly for a long time. The last glacial maximum, the deepest freeze of the most recent ice age, had peaked around 26,000 years ago. At that point, ice sheets covered enormous portions of the northern hemisphere in ways that are almost impossible to picture from where we sit now. A sheet of ice more than a mile thick sat over most of what is now Canada. It buried the Great Lakes region, pressed down into what is now the northern United States, and extended fingers of frozen mass southward across the landscape. In Europe, ice covered Scandinavia and Britain, and reached well into what is now Germany and Poland. Glaciers filled the Alps, the Pyrenees, the Highlands of Scotland. Greenland was, as it still is, locked under a vast dome of ice. But it was also colder, deeper, more extensive than anything we'd call normal today. Sea levels were dramatically lower, not by a few feet, but by around 120 metres at the glacial maximum. That changes everything about the geography of the world. Britain wasn't an island. It was connected to continental Europe by a broad plain now lying under the North Sea. Much of the shallow continental shelf around the world was exposed and walkable. The Bering Land Bridge between Siberia and Alaska was a genuine landscape, wide enough to support entire ecosystems, which is part of how people got to the Americas in the first place. The coastlines of Southeast Asia looked completely different. Indonesia and Australia were far less separated than they are today. The world's oceans were smaller, colder, and more locked up in ice. But by 15,000 years ago, the thaw was genuinely underway. Something had shifted in the balance of orbital mechanics, in the way the Earth tilted and wobbled relative to the Sun, and the northern hemisphere was receiving more solar energy. Not a huge amount more. Enough. The ice sheets began to retreat. Slowly at first, then faster, meltwater started pouring off the glaciers in volumes that are hard to think about clearly. Enormous rivers of cold, silty water draining into the oceans, raising sea levels, carving new channels, filling valleys that had been dry for millennia. By around 13,000 years ago, the world had already warmed significantly from its glacial peak. The ice sheet over North America, which geologists call the Laurentide, was still enormous, still covering vast territories across Canada, but its southern margins were retreating northward. Between the ice and the fully vegetated lands to the south, there was a shifting patchwork of terrain. Tundra giving way to open spruce woodland. Spruce giving way to denser forest as you moved further south and east. Megafauna, mammoths and mastodons and giant ground sloths and horses and camels were still roaming much of North America, though their numbers were already under pressure from both the changing climate and the arrival of human hunters. In Europe, the picture was similar. The great Scandinavian ice sheet was pulling back toward the north. The treeless tundra steppe that had stretched across much of the continent was being replaced, patchily and unevenly, by woodland. Birch and pine moving in from refugia in the south and east, colonizing newly exposed ground, changing the character of the landscape. Animals were following the vegetation north. Reindeer that had grazed across France and Spain were shifting their range. Human populations who had built their entire way of life around those herds were having to adapt, move, rethink. The North Atlantic itself was changing during the glacial maximum. Sea ice had extended much further south than it does today, covering huge stretches of the ocean surface for much of the year. That sea ice had a profound effect on European climate, blocking evaporation, reducing moisture in the atmosphere, deflecting storm tracks southward. As the ice pulled back, the ocean began to behave differently. It warmed at the surface, at least in some regions. Atmospheric circulation patterns shifted. Westerly winds began to carry more moisture into Europe. Rainfall increased in some places that had been arid. The whole system was recalibrating. And here is the thing about a climate system in transition. It's not just changing, it's also becoming more sensitive, more vulnerable. When the Earth is locked deep in a glacial state, it's in a kind of stable configuration, cold and frozen and locked in place. When it's in a warm interglacial state, it's stable in a different way. But when it's moving between those two states, when the ice sheets are melting and meltwater is flowing, and ocean temperatures are shifting, and atmospheric patterns are reorganizing, the system is full of feedbacks and tipping points that haven't settled into a new equilibrium yet. It's fragile in ways that a stable climate is not. Think of it like a table that's been tilted slowly to one side over a long time. The objects on it have adjusted, they've slid, they've settled into new positions. But the table is still tilting. Everything is in a kind of dynamic tension. A small additional push at the right moment in the right place can send things sliding in ways that a push of the same size wouldn't manage at a more stable angle. The world of 13,000 years ago was that table mid-tilt. Vegetation was moving, but not uniformly. Some regions were foresting quickly. Others were lagging behind. Rainfall patterns were shifting in ways that didn't always match the temperature changes. The big ocean circulation system that moves warm water from the tropics northward into the Atlantic, a system we'll spend a lot of time thinking about, was operating under unusual stress. It was being fed by the normal temperature and salinity gradients that drive it, but it was also receiving increasing pulses of cold, fresh meltwater from the retreating ice sheets. Fresh water is less dense than salt water. It doesn't sink the way the cold, salty water at the North Atlantic normally does, and the sinking of that cold, salty water is what drives the circulation in the first place. The system was, in a sense, fighting against its own inputs. So when the Younger Dryas hit, it wasn't hitting a stable world. It was hitting a world already off balance, already reorganizing, already in the middle of a transformation that had no guarantee of going smoothly. And the reversal, when it came, cascaded through all of those existing tensions at once. The warming that had been bringing the trees north, melting the ice, changing the rainfall, shifting the winds, all of that stalled or reversed. And the systems that had been mid-adjustment suddenly had to absorb a new shock on top of everything they were already navigating. That's part of why the Younger Dryas was so disruptive, not just because it was cold, but because it arrived in a moment of maximum vulnerability. A world that had been almost ready to fully warm, almost ready to settle into something new, was suddenly dragged backward, and everything that had been moving in one direction, the forests, the animals, the people, the ocean currents, was thrown into confusion. Understanding all of that sets up the central question more sharply. What was powerful enough to do that? When scientists say the Younger Dryas happened, they're not repeating an old legend. They're reading something written in the planet itself. And the strange thing is how consistent that writing is, even when it's recorded in completely different materials, in different parts of the world, by different processes. The clearest record comes from ice, deep, ancient ice that has been quietly stacking up, snowflake by snowflake, for more than 100,000 years. If you stand on the central plateau of Greenland today, you're standing on a time machine. Under your feet, more than 2 miles down, there are layers of ice that formed when mammoths were still walking around Europe. Layers that formed when the last glacial maximum was just beginning. Layers that formed during the Younger Dryas. Over decades of work, teams of scientists drilled through that ice. Not one team, and not one hole, but multiple cores in different places, each one a long frozen cylinder of compacted snow, hauled up in sections and stored like priceless scrolls. When they brought those cores back to the lab and began to analyze them, a pattern emerged. Each year's snowfall, compacted to a thin layer of ice, contains a chemical fingerprint of the air and the water from which it formed. You can measure the ratio of different forms of oxygen and hydrogen in the ice, what scientists call isotopes. The lighter forms evaporate more easily, the heavier ones condense more readily, and the exact balance that gets locked into the snow depends on temperature. Colder years leave a slightly different isotopic signature than warmer years. So when you measure those ratios, millimeter by millimeter, down a core, you're essentially reading a temperature graph through time. And in those Greenland cores, when you reach the period around 12,900 years ago, you see something abrupt. The isotope values, which had been trending toward warmer conditions as the Ice Age ended, suddenly swing back toward colder conditions. Not a little wobble, a sharp step, and they don't drift gently back again. They stay cold for more than 1,000 years, then jump back toward warmth almost as abruptly as they left it. That pattern is the Younger Dryas in the language of the ice. But the ice preserves more than temperature. It also traps dust, ash, microscopic salts, even tiny bubbles of ancient air. Some of the layers that form during the Younger Dryas are dustier than the layers above and below them. More dust often means drier, windier conditions at the source regions, consistent with a step back toward a more glacial-style climate across parts of the northern hemisphere. And the bubbles, those are little time capsules of the atmosphere itself. They let researchers measure past concentrations of greenhouse gases, like carbon dioxide and methane. Interestingly, the Younger Dryas cold snap appears in those gas records too, though not always in perfect lockstep with the temperature changes. Methane, which is strongly influenced by wetlands, tends to drop when those wet, warm environments shrink under colder conditions, then rise again when warmth returns. The timing of those shifts helps confirm that what the isotopes are seeing really is a large-scale climate event, not just some local quirk in Greenland. Still, ice is only one archive. If all we had were Greenland cores, we might suspect this was a purely local North Atlantic phenomenon. Cold air pouring off the ice sheet, perhaps making that region miserable, while the rest of the world went on its way. So scientists went looking for the same story in completely different materials. They found it on the seafloor. As sediments slowly settle to the bottom of the oceans, they build up in layers just like snow on ice. In many places, those layers are fine enough to preserve changes on the scale of decades to centuries. They're made of tiny particles of mud and silt, but they're also full of microfossils, shells of plankton, remains of algae, chemical traces left by organisms that lived and died at the ocean's surface. Some of those microorganisms build their shells using oxygen and carbon from the seawater around them. Just like snow forming in the atmosphere, the exact isotopic mix they incorporate depends on temperature and on the state of the water. So when researchers take a core of seafloor mud and carefully separate out these microscopic shells, they can reconstruct what the surface ocean was like when those organisms were alive. In cores taken from the North Atlantic, a pattern emerges that lines up with the Greenland ice. As the last ice age ends, surface waters in certain regions warm. Then, at about the same time, the ice cores show their temperature drop. Those planktonic records show the ocean cooling again. Other chemical indicators like the ratios of certain elements dissolved in the shells hint at changes in salinity and circulation. The Atlantic's great conveyor belt seems to have faltered or reorganized right when the Younger Dryas began. Lakes keep their own memories as well. In some lakes, especially those with calm, deep basins and limited disturbance, sediments build up in distinct annual layers called varves. One light band for each summer, one dark band for each winter, stacked like pages in a diary. Where these are preserved, they're astonishingly detailed. You can literally count years, one by one, back through time. And you can examine how the composition of those layers changes. More organic rich, dark layers often represent productive, warmer growing seasons. Pale, mineral-rich layers can indicate colder, more glacial conditions, with more rock flour washing in from surrounding landscapes. In several lakes around the North Atlantic region, those varves show a sudden switch around the Younger Dryas boundary. A change in the type of pollen preserved in the mud, from species that prefer milder climates to those adapted to colder ones, shifts in the kinds of algae and insects whose remains settle to the bottom. The lakes are reacting to the same climate shift that shows up in the ice and the seas. There are even tree rings that whisper the story, though here the evidence is thinner because 12,800 years is old for a tree. No single tree lives that long. What scientists can do instead is build chronologies by overlapping ring patterns from many pieces of wood. You match the pattern of wide and narrow rings year by year, so that older dead wood extends the record back beyond the lifespan of any living tree. In some regions, especially Europe, these chronologies now reach back toward the end of the last ice age. Individual trees don't tell you global climate, but they do respond to local warmth, cold, drought, and moisture. Periods that match the Younger Dryas interval often show stressed growth in some areas, and expansion of cold-tolerant species in others. It's a supporting line of evidence, less continuous at that age than ice and ocean cores, but still part of the same overall pattern. Tying all these different records together is its own challenge. Knowing that something happened is one thing. Knowing that it happened everywhere at roughly the same time is another. That's where timing tools come in. For materials that contain carbon, charcoal, bone, plant fragments, researchers use radiocarbon dating. Living things constantly exchange carbon with the atmosphere. including a small amount of radioactive carbon-14 produced by cosmic rays. When they die, that exchange stops, and the carbon-14 slowly decays. By measuring how much remains, you can estimate how long it's been since the organism died. But the rate of carbon-14 production in the atmosphere hasn't been perfectly constant, so raw radiocarbon ages aren't precise calendar years. They have to be calibrated using other records that are precisely dated, like tree rings and certain lake varves. Over the last few decades, those calibration curves have improved dramatically, letting scientists assign more accurate calendar ages to events around the Younger Dryas boundary. In lakes with varves, you can count the years directly across the transition from warm to cold to warm again. In ice cores, layer counting and other methods give you an independent timescale. In some fortunate cases, you can even identify specific volcanic ash layers, thin bands of glassy particles that can be traced across wide regions and dated by other means, acting as time markers that sync different archives together. When scientists line up those independent clocks, the picture becomes sharper. The cooling associated with the Younger Dryas doesn't appear scattered and random. It clusters around a narrow window. Within the limits of each method's uncertainty, the shift appears to have happened almost simultaneously across much of the North Atlantic region, with echoes in many other parts of the world. This brings us to the idea that the temperature dropped overnight. Scientifically, nobody thinks you would have gone to bed one warm evening and woken up the next morning in a blizzard that never ended. Climate, even when it moves quickly, still needs time to rearrange oceans, ice, and atmosphere. But in geological terms, fast and slow are very different from our daily experience. A transition that unfolds over a few years or a few decades is almost instantaneous compared to the tens of thousands of years it took the ice sheets to grow and retreat. Even a shift over a century is a heartbeat in the rhythm of glacial cycles. The records we have, the ice layers, the sediment cores, the lake varves don't always have the resolution to separate a 5-year change from a 50-year one at that distance in the past. What they do show is a step-like change rather than a gradual slope. A bend in the curve, not a smooth arc. So when we say the world's temperature dropped overnight, what we really mean is that, from the perspective of Earth's long, slow heartbeat, the Younger Dryas arrived in a single sudden beat. The system lurched into a different state over a span of time that could easily fit within a few human lifetimes, perhaps even within a single one. For the people and animals living through it, it would not have felt abstract. Winters lengthening, summers failing, forests stalling or retreating. Routes that had been reliable for generations growing harsher, riskier. Not a single night, but a season that never quite ended, stretching into years, then decades, until the world turned colder became the new normal. And because we can see that change so clearly in the planet's own diaries, we know it wasn't just a story. It was a real, physical event. The question, still hanging in the cold air at the end of that sudden step, is what flipped the switch. When that switch flipped, it didn't just nudge the thermostat down a notch. It reconfigured the whole pattern of how heat and water moved around the planet. If you were standing somewhere around the North Atlantic as the Younger Dryas took hold, you wouldn't have seen a neat, uniform temperature drop pasted evenly across the map. What you would have noticed instead was a change in character. The feel of the seasons, the behavior of storms, the reliability of rain and snow. The clearest shift, as far as we can tell, was in and around the North Atlantic region. Europe, Greenland, the North American side of the Atlantic, parts of the Arctic. These areas saw the sharpest cooling. In some reconstructions, winter temperatures in parts of northern Europe and Greenland plunged by 5 to 10 degrees Celsius compared to the warm-up that had just been underway. Summers likely cooled too, though not always by as much. But cooling wasn't equal everywhere. Farther south, in the tropics, the story is more complicated. In some places, temperatures changed only modestly. In others, they might even have warmed slightly. Antarctica, at the opposite end of the globe, seems to have been doing something different again, with some records suggesting a gentle warming trend continuing even while the North was snapping back toward Ice Age conditions. So the phrase Earth's temperature dropped overnight hides a lot of detail. The global average may not have crashed as dramatically as the Greenland cores suggest. What really changed fast was the distribution of heat, where it was stored, where it was released, which regions got the brunt of the cold and which ones were spared. One of the most visible symptoms of this rearrangement would have been sea ice. Modern satellite records show that sea ice can respond quickly to changes in temperature and ocean circulation, shift currents or winds slightly, and ice can expand or retreat dramatically in just a few years. During the Younger Dryas, evidence from marine sediments and ice-rafted debris suggests that sea ice in the North Atlantic spread farther south and stayed longer through the year. Imagine the ocean's winter boundary between open water and solid ice edging down toward latitudes that had recently been ice-free, not just for a few freak seasons, but as a persistent new pattern. That change matters because sea ice doesn't just float there passively. It reflects sunlight instead of absorbing it. It keeps the air above it colder and drier. It alters where heat and moisture can escape from the ocean into the atmosphere. As sea ice expanded, the usual storm tracks, the preferred paths taken by low-pressure systems and their attendant winds and precipitation, seem to have shifted. In a warmer North Atlantic, before the Younger Dryas, the jet stream and its storms may have favoured certain routes, bringing relatively mild, moist air into parts of Europe and eastern North America. With the surface ocean cooling and sea ice pushing southward, those pathways would have been bent or displaced. Storms might have been diverted, their strength redistributed. Some regions probably found themselves under more frequent, intense winter storms, as cold air flowed over relatively warm water just beyond the edge of the ice. Others may have slipped into the shadow of those changes with fewer storms, calmer skies, and deeper cold settling in. This rearrangement of heat and wind patterns helps explain another striking feature of the Younger Dryas, the patchwork of wet and dry. Climate isn't just temperature, it's also about where the water goes, how often it rains, how long snow stays on the ground, how swollen rivers become in spring, and how low they sink by late summer. In the Younger Dryas records you see lakes drying out in some areas, while others show signs of becoming wetter. In parts of the Mediterranean and the Near East, for example, some lake levels appear to have dropped, suggesting drier conditions, even as regions closer to the North Atlantic became more glacial in character. Monsoon systems, powered by the contrast between land and sea temperatures, also seem to have shifted. In some tropical regions, speleothems, mineral deposits in caves that grow in response to dripping water, record weaker monsoon rains during the Younger Dryas. In others, the pattern is more complex, hinting at reorganized rainfall belts rather than a simple global drying. For people on the ground, this didn't show up as a number on a graph. It showed up as rivers that failed to flood on schedule, pastures that didn't green as they had for grandparents and great-grandparents, or, in other places, as new wetlands forming where there had once been drier plains. The difference between temperature and climate becomes important here. Temperature is a snapshot, a reading on a thermometer at a given time and place. Climate is the long-term pattern, the average of those readings, but also the range, the extremes, the timing of seasons. During the Younger Dryas, it's very likely that the average annual temperatures fell sharply in many northern regions. But a person wouldn't experience that as -3 degrees on the annual mean. They would notice that spring arrived later than expected, and that when summer finally came, it might be shorter, cooler, and less reliable. Some years might still have been relatively warm, but the odds would have shifted. Cold years would become more common, harsh winters more frequent. Extremes matter too, Even if the average summer was only a little cooler, more frequent late frosts could ruin crops. A few monstrous winter storms each decade could reshape coastlines, topple forests, and etch themselves into oral memory. The regional differences matter just as much. One valley might grow drier, its lakes shrinking, its soils turning dusty under stronger winds. A few hundred miles away, another basin might become wetter, rivers cutting deeper channels as meltwater pulses waxed and waned. From space, the overall pattern might look like a climate state change. From the ground, it would look like 1,000 local stories, each with its own version of the same underlying shift. All of this, the abrupt cooling in the North Atlantic, the sea ice spread, the storm track shifts, the hydrological patchwork, is a clue to something deeper about how Earth's climate works. It suggests that the system doesn't always glide smoothly from one condition to another. Sometimes it moves more like a kayak crossing a line of rapids, stable as long as it stays upright, but with tipping points that, once crossed, send it suddenly into a different orientation. Climate scientists call these threshold behaviors. In a system with many interacting parts, oceans, ice sheets, atmosphere, vegetation, there are certain configurations that are stable and others that are not. If you push the system gently, it may lean, but then spring back. Push it just a little farther, and it may slip into an entirely different arrangement. Think of a light switch for a while. As you move the switch, nothing visible happens. The room stays dark. Then, at a certain point, the contact crosses a threshold and the circuit completes. The light comes on suddenly, even though the motion of your hand was smooth. In the Younger Dryas, it appears that the climate crossed one of those thresholds. Perhaps it was the amount of fresh water entering the North Atlantic. Perhaps it was a subtle change in ocean circulation, or in the way ice sheets and atmosphere were interacting. Whatever the trigger, once the system passed that point, the rearrangement of sea ice, storms, and rainfall followed rapidly. From the standpoint of physics, that kind of abrupt shift is not only possible, it's expected in a complex system poised near multiple stable states. The climate can be like a ball resting in one of several shallow bowls on a landscape of hills and valleys. A small nudge might make it wobble. A slightly larger one can send it rolling into a neighbouring bowl, where it settles into a new pattern of temperature, winds and rain. During the Younger Dryas, the ball seems to have rolled suddenly back toward a colder configuration, especially in the North Atlantic region. For more than 1,000 years it stayed there, held by the shape of the landscape. Then, just as abruptly, it rolled again, back toward warmth. To understand why it moved when it did, and why the North Atlantic seems to have been the key, we need to look more closely at one of the planet's most important pieces of machinery, the great ocean conveyor that carries heat through the Atlantic. If you stand on the shore and look at the Atlantic, it feels endless and flat, a single body of water stretching from horizon to horizon. But under that surface, there's machinery running. Slow, quiet, but powerful enough to shape climates on 2 continents. Climate scientists sometimes call it the Atlantic meridional overturning circulation. That sounds like something out of a manual, so it's often shortened to AMOC. But in essence, it's an engine made out of water. Warm, salty water flows northward near the surface of the Atlantic, from the tropics toward higher latitudes. As it travels, it releases heat into the air. That's a big part of why Western Europe is milder than other places at similar latitudes. The ocean is literally delivering warmth like a conveyor belt. Far to the north, in the subpolar North Atlantic and the Nordic seas, that surface water cools. In winter, icy winds strip heat from it, sea ice forms, leaving the remaining water behind a little bit saltier. As the water cools and gets saltier, it becomes denser, heavier. Eventually it gets dense enough to sink. This sinking is the overturning part. Surface water goes down into the deep ocean, spreading out and flowing back southward at depth, a slow return route that completes the loop. Warm water north at the surface, cold water south in the deep. A vertical conveyor turned on its side. From space, if you could see the density of the water instead of its colour, you'd notice certain regions near Greenland, Iceland, and the Labrador Sea acting like drains in a giant bathtub. Water flows in near the top, gets heavy, and then disappears down into the depths. The power source for this engine is not a turbine or a motor, but differences in temperature and salt content, what oceanographers call thermo-haline circulation. Thermo for heat, haline for salt. Both matter because they both change density. Warm water, all else equal, is lighter than cold water. Fresh water is lighter than salty water. Out in the open Atlantic, where currents stretch for thousands of kilometres, small differences in density add up. They dictate which water floats on top and which sinks below. They determine the vertical layering of the ocean. In the high latitudes of the North Atlantic, the recipe for deep water is cold plus salty. Remove either ingredient, and the mixture doesn't work as well. This is where sea ice and fresh water come in. When sea ice forms, it doesn't take salt with it. The ice crystals are mostly fresh. The salt is left behind in the water just underneath the forming ice, making it saltier and denser. In a stable, cold climate, repeated cycles of sea ice formation and melting help maintain dense surface waters that can sink. But change the balance, and the same system can start working against deep water formation. Melt a lot of ice on land, glaciers and ice sheets, and you release large volumes of fresh water into the ocean. Open the gates of a giant proglacial lake, and you pour a flood of low salinity water onto the surface of the North Atlantic. Increase snowfall over certain areas, and you alter the pattern again. Fresh water does one simple, crucial thing. It dilutes salt. Add enough of it near the regions where deep water usually forms, and the surface layer becomes lighter. Even if it's cold, it may no longer be dense enough to sink easily. You get a lid, a cap of fresher, more buoyant water that sits on top of the denser layers below. At the same time, expand sea ice far enough south, and you can block the regions where heat used to escape, and where that dense water used to form. You change the points where the engine can breathe. In models and in some modern observations, this kind of freshening tends to do two things. First, it slows the overturning. If the water is lighter, it sinks more sluggishly. The entire conveyor belt responds. Less warm water pulled northward at the surface, less cold water sent back at depth. The flow rate drops. Second, it can push the system toward a different configuration. Not just a weaker version of the same pattern, but a distinct mode where deep water formation shifts location or becomes far more intermittent, or, in the most extreme simulations, largely shuts down in the northern basin. In the context of deglaciation, this matters. At the end of the last ice age, enormous ice sheets fringed North America and northern Europe. As they melted, they didn't release fresh water steadily, like a tap turned on low. They carved icebergs. They pondered water in vast meltwater lakes, dammed against the ice. They failed suddenly, sending torrents into the ocean through newly opened channels. Climate models that simulate these conditions show something interesting. When you start with a strong overturning circulation and then gradually warm the world, the AMOC doesn't always decline smoothly. Instead, there are parameter ranges where it behaves like that light switch. Below a certain freshwater input, the circulation wobbles but persists. Add just a bit more, past a threshold, and the pattern flips. The engine collapses into a weaker state, or reorganizes, while the rest of the climate system adjusts around it. During deglaciation, this kind of tipping behavior becomes more likely, because so many of the ingredients are changing at once. Background temperatures, ice sheet size, sea level, storm tracks. even the shape of coastlines and basins that guide currents. The North Atlantic is not a static tub of water, it's a basin being reshaped in real time, while the engine inside it is still running. In many simulations designed to reproduce the Younger Dryas, when you dump a large pulse of fresh water into the North Atlantic, especially into areas feeding the subpolar gyre and the Nordic seas, the modelled amok weakens strongly. Greenland and much of the North Atlantic region cool in response. Sea ice spreads, precipitation patterns shift. The result looks, in broad strokes, a lot like the Younger Dryas fingerprint. That resemblance is one reason this mechanism became the leading framework for thinking about what happened. It offers a way to connect several observations that might otherwise seem unrelated. The abrupt cooling around the North Atlantic, the spread of sea ice, the changes in storm tracks and rainfall belts, the asynchronous behaviour of the two hemispheres, with the north plunging back toward glacial conditions, while parts of the south continue to edge warmer. If the Atlantic engine stumbles, the consequences ripple outward, cool the North Atlantic surface by reducing the northward heat transport, and the atmosphere above it adjusts. The jet stream shifts. Tropical rain belts like the intertropical convergence zone can move southward. Monsoons may weaken or reorganize. Meanwhile, changes in the deep ocean take centuries to millennia to propagate, feeding back into the Southern Ocean and Antarctic climate. The AMOC hypothesis also fits with what we know from other abrupt events. In earlier parts of the last glacial period, there were episodes known as Heinrich events, where armadas of icebergs appear to have surged into the North Atlantic, dropping layers of rock debris onto the seafloor. These events are often associated in the records with rapid cooling in the North Atlantic and rearrangements in global climate. Freshwater and ice input disturbing the Atlantic engine, climate responding abruptly. By the time researchers began seriously puzzling over the Younger Dryas in the late 20th century, this idea of a sensitive Atlantic overturning system was already emerging. The ocean was not just a passive backdrop, but an active player, with its own thresholds. The Younger Dryas seemed to fit that pattern almost too well. A world in the middle of a deglaciation, ice sheets shrinking, giant lakes perched against their flanks, meltwater routing toward the North Atlantic. A sudden cool snap focused in that very region, with signs of altered deep water formation in marine cores. It was natural to picture the AMOC as the hinge. Push it with fresh water just enough, and the hinge snaps into a colder position. The sea ice grows, the winds respond, and the climate of the North Atlantic world changes in a matter of decades. But a mechanism, no matter how elegant, is only part of the story. For the Atlantic engine to stumble, something had to pull the pin. Fresh water had to get into the right place, in the right amount, at the right time. And when you look closely at the geological record, tracing ancient rivers and vanished lakes, that neat picture starts to blur. To see why, we have to follow the water itself, out of the ice sheets, into the lakes, and along the paths it might have taken to the sea. If you rewind the map of North America to the end of the last ice age, coastlines crawl inward, sea level drops, and something else begins to appear in the interior, water that has nowhere to go. As the Laurentide ice sheet thinned and retreated, it didn't melt like a neat, even puddle. It slumped and sagged. Its enormous weight had depressed the crust beneath it for tens of thousands of years. Where the ice margin pulled back, that warped landscape often sat below the level of the outlets that would eventually drain it. So meltwater pooled along the southern and western edges of the ice, trapped between high ground and a wall of glacial ice. Rivers that once flowed north into what is now Hudson Bay, or east into the St. Lawrence, found their routes blocked. Instead of carving their way through, they filled low-lying basins into shallow seas. Geologists call these proglacial lakes bodies of water backed up against ice margins, dammed not by bedrock but by frozen walls. The most famous of them is Lake Agassiz. At its maximum, Lake Agassiz sprawled across what is now much of Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. Picture a lake larger than any on Earth today, wider than all of the modern Great Lakes combined, stretching to the horizon in every direction, its northern shoreline a moving front of ice. Agassiz didn't just sit quietly. Its level rose and fell as meltwater input changed, as the ice sheet advanced or retreated, and as different outlets opened and closed. At times it drained south into the Mississippi system, sending its water toward the Gulf of Mexico. At other times it appears to have escaped eastward toward the St. Lawrence, or northward toward Hudson Bay. This instability is central to the Younger Dryas story. An ice dam is not a permanent structure. It doesn't have the reassuring solidity of stone. It is more like a frozen sandbag wall placed across a river that is constantly trying to undercut it. Warm summers, rising meltwater, creeping fractures, all of these weaken the barrier. In modern times, when smaller glacial lakes have formed behind ice dams in mountain regions, they have sometimes failed catastrophically. One day the lake is there, the next a channel has cut through the ice or along its base, and a wall of water and ice surges downstream. At the continental scale, something similar could happen with lakes like Agassiz. The leading versions of the freshwater trigger idea imagine an abrupt rerouting event, a moment when one of these giant lakes, or a chain of them, suddenly gained access to a new path to the ocean. A channel cut under the ice, a low divide breached, a dam overtopped and then eaten away too quickly to stabilize. In this picture, Agassiz, or a related system of lakes sometimes lumped together as Agassiz Ojibwe, is the loaded reservoir. The North Atlantic and Arctic gateways are the vulnerable targets. If a large enough volume of low salinity water poured rapidly into the Labrador Sea, Hudson Strait, or the regions feeding the subpolar gyre, it could freshen the ocean surface there dramatically. Not a gentle dilution spread over millennia, but a pulse, a few years or decades, where the salinity in the key deepwater formation zones dropped far below normal. In the language of the previous section, someone would have pulled the density rug out from under the Atlantic engine. Cold but unusually fresh surface water would resist sinking. Sea ice, favoured by the cooling and freshening, would extend farther, creating a lid over areas that once breathed heat into the sky. The overturning cell would weaken, less warm water would travel north, more heat would instead remain in the southern hemisphere and lower latitudes. The climate response would radiate outward. Models show that you don't have to change the whole global ocean to get this effect. You just have to hit the right spot hard enough, at the right time. But that raises the obvious question: did such a flood actually happen in the right region just as the Younger Dryas began? This is where the story shifts from clear physical intuition to messy forensic work. On land, the evidence for ancient lake outbursts often comes from geomorphology, the shapes carved into the landscape by sudden, powerful water flow. Oversized spillways cut into bedrock, where no normal river of that size could exist today. Giant current ripples, tens of meters apart, frozen in gravel plains. Abandoned shorelines etched along hillsides at consistent elevations, marking former lake levels. Around the margins of former Lake Agassiz, such features do exist. There are strand lines showing where the lake once stood. There are channels that appear to have guided water either toward the Mississippi drainage, or north toward what is now Hudson Bay, or east toward the Great Lakes and St. Lawrence. Some of these channels show signs of large, possibly rapid discharge events. Scoured bedrock, boulders moved like pebbles, sediment fans where torrents slowed at their exit. In the oceans, the fingerprints look different. Marine cores taken from the floor of the North Atlantic and Arctic margins preserve layers of mud and microscopic shells that record changes in salinity and temperature over time. The oxygen isotope ratios in foraminifera, tiny plankton with calcium carbonate shells, can shift when fresher water dilutes the surface or when temperatures change. Other isotopic systems like neodymium or strontium can hint at the source regions of that water. Some cores from near the outlets of the former Laurentide ice sheet show signs of freshening and altered deep water formation around the onset of the Younger Dryas. Others record layers that might correspond to increased sediment input from a big discharge event. Taken together, these lines of evidence have been woven into a narrative. Lake Agassiz, or its successor lake systems, grew large enough that a northern outlet suddenly opened, sending a great flood of fresh water into the Arctic North Atlantic Gateway roughly 12,900 years ago, disrupting the amok and triggering the Younger Dryas. It's an elegant story. It links the physics of the Atlantic engine with a plausible source of fresh water and a mechanism for delivering it at the right moment. But when you look closely, cracks appear. One problem lies in timing. The dates for lake levels, outlet switches, and flood deposits come from a mix of radiocarbon ages, optically stimulated luminescence dating, and correlations between terrestrial and marine records. Each method carries uncertainties. Organic material can be reworked from older deposits. Luminescence signals can be partially reset. Calibration curves may introduce wiggles of their own. Some studies have suggested that the largest documented northern outburst from the Agassiz-Ojibwe system actually occurred at the very end of the Younger Dryas, not at its beginning. That later flood might be tied to another abrupt event in the climate record, a brief, sharp feature sometimes called the Preboreal Oscillation. If that is correct, then Agassiz's most dramatic northern drainage may be too late to explain the initial Younger Dryas cooling. Other work has argued for earlier drainage episodes, or for sustained high discharge toward the North Atlantic via the St. Lawrence at roughly the right time. Still others emphasize southern routes, suggesting that for much of the critical interval, most meltwater from central North America may have flowed toward the Gulf of Mexico rather than directly into the subpolar North Atlantic. This brings us to a subtle but crucial point. In terms of climate impact, where the water went can matter as much as how much there was. If 1 million cubic kilometers of fresh water, spread over a couple of millennia, quietly found its way into the North Atlantic through broad, diffuse flow, the ocean would have time to mix and adapt. The salinity contrast would be modest. The amok might weaken gently but not flip. If that same volume were routed mostly into the Gulf of Mexico and subtropical western North Atlantic, models suggest the effect on deep water formation in the subpolar seas would be muted. The water would circulate, be warmed, evaporate, and blend before reaching the key sinking regions. By contrast, a smaller volume poured rapidly and directly into the Labrador Sea, Davis Strait, or Nordic seas could pack a much bigger punch. A short, sharp pulse can cross the threshold that a longer, slower trickle never reaches. So when paleoclimatologists argue about Lake Agassiz, they are usually not debating whether it existed or whether it sometimes drained catastrophically. Those are well established. The argument is about routing and timing. Did a major outburst send water north into the critical regions, just as the Younger Dryas began? Or were the main drainage routes pointed elsewhere? The geological record does not yet give a simple, unanimous answer. Some teams point to landforms in Manitoba and Ontario that they interpret as evidence for an early northward-directed flood into Hudson Bay just before or during the onset of the Younger Dryas. Others emphasize that clear, well-dated flood deposits in Hudson Strait appear younger, aligning better with the end of the cold period. Marine records around the subpolar North Atlantic show freshening, but correlating that precisely to particular outbursts on land is tricky. And then there is the possibility that there was never one single smoking gun flood. Instead, multiple medium-sized routing changes and outbursts, spread over centuries, might have combined with background meltwater and evolving ocean ice feedbacks to tip the Atlantic circulation over its threshold. In that view, Lake Agassiz is more like one player on a crowded stage than the lone actor delivering the crucial line. What everyone agrees on is that during deglaciation, the freshwater routing system of North America was unstable, and gigantic lakes periodically rearranged their outlets. The continent's plumbing kept changing, rivers reversed. Basins that drained south began draining north or east. Ice margins advanced and retreated, opening and closing gateways. The Younger Dryas sits right in the middle of this hydraulic chaos. To solve its mystery, researchers are not just tracking how much water melted out of the ice sheets, but following the exact paths that water took. Did it dive straight into the North Atlantic's lungs or slip around the side, dispersing harmlessly? As we trace those vanished rivers and shorelines, another clue appears, not in the lakes themselves, but in an abrupt, razor-straight boundary left on the land, a line that seems to mark the moment when something in the climate system changed almost overnight. If you walk out across some of the old lake plains left by the Ice Age, the landscape can feel almost aggressively ordinary. Flat fields, low rises, a scatter of stones. Then you scrape down into the soil, and the ordinary peels back. In many places around the northern hemisphere, if you dig through late glacial sediments, you eventually hit a transition that looks oddly sharp. Above, younger soils and river deposits that formed after the world warmed for good. Below, layers that belong to the big deglaciation, when ice sheets still loomed on the horizon. Right at the join in some sites, there is a thin dark band, centimetres thick, sometimes only a smear. This is what people mean when they talk about a Younger Dryas boundary layer. It is not a single global line you can follow, like a painted stripe around the planet. It is more like a family resemblance, similar hints showing up again and again, near the level in the ground that corresponds to around 12,900 years ago, the moment when the climate record shows that sudden drop into cold. At a number of sites in North America, Europe, and the Middle East, researchers have reported that this boundary layer contains unusual concentrations of certain materials. Charcoal, for one, tiny black fragments mixed into the sediment, suggesting widespread burning of vegetation at or just before the onset of the Younger Dryas. Also, microscopic spheres, microspherules, made of glassy or metallic material. Under a microscope, these can look like little beads or droplets. Some are rich in iron, others contain melt textures that suggest rapid heating and cooling. And then there is the geochemistry. Elevated levels of elements like iridium, platinum, or other metals that are rare in ordinary crustal rocks, but more common in meteorites or in material heated to very high temperatures. In some reports, magnetic grains with unusual compositions cluster right at the boundary horizon. To some researchers, this constellation of features looks suspiciously like the fallout from something violent. Intense wildfires, high-temperature melting, maybe even an impact or airburst from space. To understand why that idea is controversial, it helps to slow down and think about how layers in the ground form in the first place. Stratigraphy, the study of sediment layers, is built on a simple principle. In undisturbed deposits, younger material lies on top of older material. Over time, rivers lay down sand and silt. Lakes collect mud. Wind piles up dust. Peat accumulates in wetlands. Each environment builds its own stack of layers, like pages in a very slow, very fragile book. But unlike a book, the pages are not safe once they are written. They can be torn, folded, smeared, and recopied. Animals burrow through sediments. Plant roots push down, bringing material up and sending material deeper. Floods cut channels and then backfill them. Waves chew away at shorelines and redeposit old sediment in new places. Glaciers bulldoze entire landscapes and drop their cargo haphazardly when they melt. This constant stirring is called mixing or reworking. It means that not every sharp change you see in a core or an exposure necessarily represents a single moment in time. Sometimes a boundary can be a composite, made of material that was eroded from older layers and dumped into a younger one. Charcoal provides a good example. Forest and grassland fires have been happening for millions of years. Their remains, tiny burned fragments, can be washed downstream, blown by wind, or incorporated into soils long after the flames have gone out. A flood that cuts into older charcoal-rich deposits and then lays them down again in a new layer can create the illusion of a sudden pulse of burning, even if the source charcoal was originally produced over centuries. Microspherules and unusual geochemistry can also be misleading if you do not know precisely where they came from. Industrial pollution in the modern era rains down metallic particles over large regions. Volcanic eruptions can create their own tiny glass beads and enrich sediments in trace elements. Then those particles can be reworked just like charcoal. So, when researchers claim to find a distinctive cocktail of charcoal, microspherules and anomalous metals right at the Younger Dryas boundary, other scientists ask careful questions. How well constrained is the age of that particular layer? Could the particles have been moved there from older or younger deposits? Are the same patterns really present at many sites, or only at a few? This is where the dream of a clean, global Younger Dryas boundary line runs into the messy reality of geology. Correlating a single horizon across a continent, let alone between continents, is difficult even under ideal conditions. You need multiple, independent ways of tying layers together. Radiocarbon dates from embedded organic material, volcanic ash layers with unique chemical fingerprints, paleomagnetic markers, or clear fossil assemblages that change at known times. For the late glacial period, some of these tools exist. There are radiocarbon sequences. In a few regions, there are volcanic ash layers that can be matched over long distances. There are pollen records showing when particular plant communities shifted. But the exact onset of the Younger Dryas does not line up perfectly in every archive. Lakes respond at slightly different times than oceans. Soils may lag behind the atmosphere. Ice cores give lovely high-resolution timelines, but matching a soil horizon in New Mexico to a particular wiggle in a Greenland ice core is an exercise in inference, not direct observation. Against that background of uncertainty, the reports of a special Younger Dryas boundary layer sit on a knife-edged. Supporters argue that the repeated appearance of similar materials, peaks in charcoal, clusters of microspherules, unusual metal ratios, at roughly the same time in many different places, hints at some kind of global-scale disturbance. Critics counter that when sampling methods, counting procedures and dates are scrutinized. Some of those peaks shrink, shift, or vanish. In some locations, later work has failed to replicate the original findings. In others, the boundary turns out to be thicker and more time-averaged than first thought. What initially looked like the residue of a single night or a single year sometimes turns into a blurred smear spanning decades or centuries. So what would strong, repeatable evidence for a special Younger Dryas boundary really look like? First, it would show up independently in many well-dated sequences around the world, not just at a handful of favoured sites. The same narrow time slice within, say, a human lifetime or two, would have to be pinpointed in lake muds, peat bogs, marine cores and soils, all agreeing within their dating uncertainties. Second, the unusual materials would need to have a clear, consistent signature. The same types of microspherules with the same internal structures and chemical fingerprints, turning up again and again. The same pattern of metal enrichment, distinguishable from both natural background variability and modern contamination. Third, the layer would need to be demonstrably primary, not made mostly of reworked older material. That means looking at how the particles are embedded, whether the layer cross-cuts other features, whether burrows disturb it, and whether there are signs of erosion at its base. Finally, the supposed boundary would need to connect convincingly with what we know from the climate archives. A distinct physical horizon in the ground should line up, within error, with the first big step in cooling recorded in ice cores, tree rings, and other high-resolution climate proxies. If such a horizon exists, if the Earth really does carry a thin, nearly synchronous line marking the moment the Younger Dryas began, we have not yet mapped it with the clarity of, say, the layer left by the asteroid that ended the age of dinosaurs. What we have instead are hints, dark smudges in the soil, spikes in certain elements, tiny glassy drops under the microscope. Enough to provoke hypotheses about what might have happened, but not enough to close the case. And one of those hypotheses is bold. It suggests that the sudden boundary in the ground is not just a record of shifting winds or reorganized oceans, but the scar of something that came from above, a moment when the sky itself joined the story of the Younger Dryas. The idea goes like this. Around 12,800 years ago, as the big ice sheets were melting and the North Atlantic was already in a delicate mood, something large and fast arrived from space. Not a dinosaur killer the size of a city, but a comet or a swarm of comet fragments, maybe tens or hundreds of meters across each, breaking apart in the atmosphere or slamming into the ice. The collisions in this picture would have been spectacularly violent on a regional scale. Airbursts over the ice sheets, fireballs over forests, shock waves and thermal radiation ripping across the landscape, vast plumes of vaporized ice, rock and soil shooting into the sky. Supporters of this idea picture a chain reaction. The impacts ignite wildfires over large areas of North America, and perhaps elsewhere. They loft soot and dust high into the atmosphere. They melt parts of the ice sheet in a rush, injecting a pulse of fresh water into the North Atlantic. The ocean's circulation, already fragile, stumbles. Within decades or even years, the climate plunges back into cold. It is a tidy story, violent, dramatic, and capable on paper of tying together burn layers, strange particles, and a sudden, global-ish chill. But space rocks don't just leave stories, they leave signatures. If a comet or a fragment storm hit the Earth with enough energy to trigger continent-scale fires and disturb ocean circulation, it should have left behind more than just a dark smear in the soil. Geologists know what to look for, because other impacts have been studied in microscopic detail. One of the main predicted markers is shocked minerals. When a high-velocity impact drives a pressure wave through crustal rock, the crystal lattices of minerals like quartz can deform in distinctive ways. Under a microscope, these shock features have a kind of barcode pattern, planar deformation structures that ordinary volcanic eruptions or tectonic stresses almost never produce. Another clue would be the distribution of certain elements. Meteorites and comets often carry higher proportions of iridium, platinum, and some other metals than typical crustal rocks. At the boundary where the asteroid that ended the Cretaceous hit, a thin layer enriched in iridium wraps the globe like a thin, invisible ring. Alongside those, you might expect tiny particles created by the intense heat of impact, melt glass, microspherules with particular textures, and in some conditions, nanodiamonds, minute diamond crystals that can form under shock. You would also look for physical scars, craters, depressions with evidence of high-energy formation. Maybe not a single enormous crater, because an object fragmenting in the atmosphere can create many smaller explosions, but at least a few candidates with ages clustering around 12,800 years ago. That is the wish list. Advocates of what is often called the Younger Dryas impact hypothesis argue that many items on that list are present. They point to peaks in platinum and other metals in Greenland ice cores and in sediments from North America and Europe. They highlight reports of microscopic diamonds and purportedly shocked minerals in the Younger Dryas boundary layer. They emphasize clusters of particular microspherules, glassy and metallic beads that, in their view, show evidence of extremely rapid melting and cooling. They also argue that some unusual landforms, such as certain elliptical depressions along the Atlantic coastal plain of the United States, could be remnants of oblique impacts into ice or saturated ground, later modified by erosion. From their perspective, the pattern is compelling. A temporally narrow dark layer, coinciding with the onset of cooling. Charcoal spikes suggesting immense fires. Exotic particles and metal anomalies hinting at high-temperature, high-energy events, all arriving in the stratigraphic record just when the climate takes its strange, abrupt turn. Critics see something different. They note that many of the claimed markers are not unique to impacts. Nanodiamonds can form in a variety of high-energy conditions, including ordinary fires and industrial processes. Some features that were initially described as shocked quartz have later been reinterpreted as deformation from more mundane geological stresses, or not shock features at all. When independent labs have gone hunting for the same signals, the results have often been mixed. In some follow-up studies, attempts to replicate the reported nanodiamond peaks at the Younger Dryas boundary have failed. The particles either are not found, or they appear in similar amounts above and below the supposed layer. Microspherules that were initially reported as unusually abundant near 12,800 years ago sometimes turn out, under different counting methods, to be more evenly distributed through time. Even the metal anomalies have become points of debate. In some lake cores, platinum and iridium spikes do appear near the onset of the Younger Dryas. In others, similar spikes crop up at times when no impact is suspected, perhaps linked to volcanic fallout or other processes. What looks like an impact fingerprint in one sequence can look like ordinary noise in another. The crater problem is another sticking point. There is at least one intriguing feature buried under the ice of northwest Greenland and known as the Hiawatha crater that has been proposed as a possible Younger Dryas age impact. Radar imaging reveals a roughly circular structure more than 30 kilometers across, with shapes suggestive of a high-energy collision. But the age of Hiawatha is not well pinned down. Some studies suggest it could be much older than 12,800 years. Others argue for a younger date, but with large uncertainties. Until its age is firmly established, it cannot play a starring role in the Younger Dryas story. Other proposed impact structures have faced similar issues: ambiguous morphologies, weak or conflicting age constraints, or alternative explanations that do not require something falling from space. Behind the technical arguments lies a deeper methodological problem. Most of the proposed evidence for a Younger Dryas impact comes from what scientists call proxies, indirect indicators. Charcoal for fire, microspherules for high-temperature melting, certain geochemical ratios for extraterrestrial input, nanodiamonds for shock. Each of these proxies can be noisy. Each can have multiple possible sources, and each demands careful, reproducible measurement. If you rely too heavily on any one of them, especially at the edge of their interpretive power, you run the risk of building a large narrative on a small foundation. This is why replication has become a central battleground. For an extraordinary claim that a cometary encounter helped flip the climate back into near-glacial conditions, you need more than a one-time detection in a few cores handled by one research group. You would want different laboratories using different techniques on sediments collected independently from many regions to converge on the same conclusion. You would want the nanodiamonds, the shocked grains, the microspherules and the metal enrichments all telling the same story at the same time, with the same timing as the climate shift seen in ice and tree rings. And you would want alternative explanations: volcanism, reworking, slow accumulation of fire residues, industrial contamination in younger layers to be thoroughly ruled out, not just mentioned and waved away. The philosophy here is simple, even if the chemistry and stratigraphy are not. Big, disruptive ideas in science are not forbidden. They are welcomed, but they must work harder. The more dramatic the claim, a cosmic impact helped trigger a global climate event, just as humans were spreading across the continents, the more it has to be nailed down by independent, converging lines of evidence. For the Younger Dryas impact hypothesis, that convergence is not yet there in a way that convinces most specialists. Some lines of evidence point one way, some another. Some datasets support the idea, others seem neutral or contradictory. Depending on which proxies you trust most, and which studies you weight more heavily, you can still come away with very different impressions. That does not mean a comet or fragments definitely did not play any role. It means that, so far, the case remains open, sitting in that uncomfortable middle ground between impossible and established. While that argument continues, it is worth remembering that impact is only one way to jolt the climate. Even without help from the sky, the Earth system has plenty of its own levers, volcanoes, subtle shifts in solar output, and feedbacks within the oceans and atmosphere that can amplify small pushes into big changes. To understand the Younger Dryas, we have to weigh those possibilities too. When people look for ways the climate can be kicked hard and fast, volcanoes are usually near the top of the list. Explosive eruptions can inject sulfur-rich gases high into the stratosphere. There, far above the weather, those gases react to form tiny sulfate aerosols that spread around the globe like a thin veil. They reflect a fraction of incoming sunlight back into space, dimming the Earth very slightly. We have seen this in action in historical time. When Mount Tambora erupted in 1815, the following year became known in parts of Europe and North America as the year without a summer, frosts in June. Snow in July, failed harvests, food shortages, strange sunsets. Tree rings from that period show a sharp, brief suppression of growth in many regions, consistent with a short, intense, cool spell. In 1991, when Mount Pinatubo erupted in the Philippines, satellites were watching. They saw the aerosol clouds spread, measured the drop in sunlight at the surface, and tracked the response of the climate system. Global average temperatures dipped by about 0.5 degrees Celsius for a couple of years, then slowly rose back as the aerosols settled out and were washed away. This is the typical pattern. A single, very large eruption can cool the planet measurably, but only for a short time, usually 2 to 5 years. Most of the aerosol load falls out of the stratosphere within a few seasons. The climate system, with its enormous thermal inertia, then drifts back toward where it was headed before. To sustain cooling for a century or more by volcanism alone, you would need a sequence of major eruptions, spaced closely enough that the atmospheric veil never really thins. A kind of volcanic drumbeat, pounding the system again and again. When researchers look at ice cores from Greenland and Antarctica, they can actually see the fingerprints of past eruptions, narrow spikes of sulfate, layer after annual layer. Around the time of the Younger Dryas onset, some spikes are indeed present. Volcanoes were still erupting, as they always are, but the pattern does not look like the required drumbeat. There is no obvious cluster of super-eruptions, no long plateau of elevated volcanic sulfate that would match the roughly 1,200-year duration of the Younger Dryas cold phase. The sulfate peaks that do exist tend to be narrow and discrete, the kind that produce short-lived coolings rather than a millennium-long regime shift. Some scientists have suggested that an especially well-placed eruption, or a few of them, might have nudged the already unstable North Atlantic over a threshold. In that scenario, the aerosols merely provide the shove. The long cold period is then maintained by ocean circulation changes and feedbacks. Volcanism in this view is the trigger, not the whole story. That kind of idea leads naturally to another lever, the sun. Solar output is not perfectly constant. It varies in cycles, the most famous being the roughly 11-year sunspot cycle during which the total solar energy reaching the top of Earth's atmosphere wobbles by about 0.1%. On longer timescales, there appear to be grand minima and maxima periods, when the sun is slightly dimmer or slightly brighter than average for several decades at a time. During the Maunder minimum in the 1600s and early 1700s, sunspots became extremely rare for several decades. That interval overlaps in Europe with some of the coldest winters of the so-called Little Ice Age. Frozen rivers, advancing alpine glaciers, harsh seasons that left their mark in paintings and chronicles. It is tempting to draw a straight line. Quiet sun, cold earth. But the connection is not quite that simple. The direct change in solar energy, even between a grand minimum and a more active phase, is small. Much of the climate response may be mediated through complex pathways, changes in the stratosphere, subtle shifts in atmospheric circulation, possible effects on cloud cover. These links are still actively studied and debated. For the time of the Younger Dryas, the picture becomes even foggier. To reconstruct past solar activity, scientists often use cosmogenic isotopes, rare forms of elements like carbon-14 and beryllium-10, produced when high-energy particles from space collide with atoms in the upper atmosphere. When the sun is more active, its magnetic field and solar wind deflect more of those cosmic rays, and production of these isotopes drops. When the sun is quieter, production rises in ice cores and tree rings spanning the last many thousands of years. These isotopes form wavy patterns that can be interpreted, cautiously, as records of solar variability. Around 12,800 years ago, those records do show structure. There are ups and downs, but they are not sharp, singular spikes that line up neatly with the sudden onset of Younger Dryas cooling. Nor do they show an obvious, prolonged solar minimum, exactly matching the cold interval's full duration. Part of the problem is resolution. Cosmogenic isotope records are smeared by atmospheric mixing, by transport in oceans and ice, by dating uncertainties. They can hint at solar moods, but they struggle to pinpoint the kind of abrupt, year-scale shift seen at the Younger Dryas boundary in Greenland ice. It is therefore difficult with current data to say that a specific solar event caused the Younger Dryas. If the sun played a role, it may have been more as a background influence, tilting the odds, modulating other processes, rather than flipping a clear on-off switch by itself. Even if the initial push was modest, the Earth system holds amplifiers. Sea ice is a powerful one. When ocean water freezes, it turns from a dark, light-absorbing surface into a bright, reflective one. Sunlight that would have warmed the sea is instead bounced back into space. The colder it gets, the more sea ice can grow. The more sea ice grows, the more sunlight is reflected, promoting further cooling. This is the ice albedo feedback. During the last glacial maximum, huge areas of the North Atlantic and Arctic Ocean were seasonally or even permanently choked with ice. By the time the planet was warming toward the Younger Dryas, those ice margins were retreating, wobbling back and forth with each decade's weather. A relatively small cooling, whether from a volcanic pulse, a brief solar dip, or a shift in ocean currents, could have allowed winter sea ice to linger longer into spring, and summer sea ice to extend just a bit farther south. That extension would have altered winds, storm tracks, and the exchange of heat and moisture between the ocean and the atmosphere. Once that feedback loop engaged, the regional climate around the North Atlantic could have locked into a much colder mode even if the original forcing waned. In this sense, the duration of the Younger Dryas cold spell may tell us as much about internal feedbacks as about the size of any external shove. This is where single-cause explanations start to struggle. If we ask one mechanism, just a volcano, or just a solar lull, or just a comet to explain everything, we quickly run into mismatches in timing, or in geographic pattern, or in the length of the event. A solitary volcanic eruption can give you a brief global chill, but not easily a 1,000-year plateau. A small change in solar output might skew climate probabilities, but it is hard to make it produce an abrupt, regional, ocean-centered reorganization at precisely 12,800 years ago. A comet impact, if it happened, would be over in seconds to hours, with an aerosol and fire signature that should fade much faster than the Younger Dryas actually lasted. The shape of the event, a sharp onset, a long cold stand, and then a relatively quick return to warming, looks more like the behaviour of a complex system snapping between internal modes than like the steady forcing of a single knob. That is why many researchers now think in terms of multifactor scenarios. In those pictures, the Earth around 12,800 years ago was already delicately balanced. Ice sheets were shrinking, meltwater routes were shifting. The Atlantic circulation was sensitive. The sun and volcanoes and greenhouse gases were all playing their slow, overlapping tunes. Into that background, one or more short-lived disturbances, a fresh pulse of meltwater, a cluster of eruptions, a modest solar dip, perhaps even an extraterrestrial nudge, could have nudged the system across a threshold. Once crossed, the feedbacks involving sea ice, ocean circulation, and atmospheric patterns could have maintained a colder state for centuries, long after the initial triggers had faded. In a sense, this makes the Younger Dryas both more and less mysterious. Less, because we do not need a single perfect smoking gun. More, because we must now untangle interacting influences, each modest on its own, but transformative in combination. And while those global levers were being pulled, something else was changing more quietly, down at the level of land and life. The ice margins were moving, forests and grasslands were shifting, whole ecosystems were being rearranged in response to the chill. To understand what that looked like on the ground, what plants grew where, and how animals and people responded, we have to zoom in again from the scale of volcanoes and solar cycles to the slower, patient reshaping of the continents themselves. When climate scientists talk about the Younger Dryas, they usually start with ice cores, ocean currents, and radiative forcing. But for anything living on land, the story showed up in a different language. It arrived as changing plants. If you could glide slowly over the northern hemisphere at the start of the Younger Dryas, you would see the continents quietly repainting themselves. Forests drawing back, grasslands thinning, low, hardy tundra plants advancing south like a slow, silent tide. In much of northern Europe, where birch and pine had been marching back after the peak of the last ice age, that advance stalled and then retreated. Pollen grains trapped in the mud of lakes and bogs record the change almost year by year. Before the cooling, those layers are rich in tree pollen. Pine, birch, hazel, a landscape of open woodland with scattered meadows and shrubs, getting greener as the climate warmed. Then, suddenly, the tree pollen drops. In its place, pollen from herbs and shrubs that specialize in cold, dry conditions begins to dominate. Artemisia, a sagebrush-type plant, grasses, little cushion plants that hug the ground. This is tundra and steppe taking over, a low, wind-swept vegetation cover, more like modern northern Scandinavia or parts of Siberia. In some regions of Central and Northern Europe, forests didn't disappear entirely. They broke apart into pockets. Islands of trees along sheltered valleys, south-facing slopes or near lakes, surrounded by open, treeless tundra and steppe. Ecologists call this kind of pattern a mosaic, not one uniform biome stretching across the horizon, but a patchwork of habitats, each responding to local conditions. North America tells a similarly complex story. South of the big ice sheets, forests that had been spreading northward into the Great Lakes region suddenly held their ground or retreated. In parts of what is now New England and southeastern Canada, pollen records show boreal species like spruce regaining territory at the expense of more temperate hardwoods. Further west, in the interior plains, grasslands hardened. In some places, they may have shifted toward colder, drier, steppe-like communities. In others, where moisture stayed relatively high, wetlands and riparian forests persisted as green lines in a cooler, more open country. The key point is that the Younger Dryas didn't paint everything the same colour. Even in the middle of this pronounced cooling, some regions stayed relatively mild and moist. Parts of the North Atlantic coast, some areas around the Mediterranean, pockets in the American West and Southwest held onto more diverse forested or shrub-dominated ecosystems. Elsewhere, especially at higher latitudes and elevations, the land pushed back toward Ice Age conditions. Zoomed out, the continents became patchy, bands of tundra stretching farther south. Forest belts squeezed and fragmented, grasslands and shrublands expanding and contracting in ways that depended on subtle combinations of temperature, precipitation, soils, and topography. Plants were not the only things that moved. Where vegetation goes, animals follow or try to. Large herbivores from reindeer in Eurasia to caribou and elk in North America tracked the advancing tundra and open steppe. Their preferred forage, cold-adapted grasses, sedges, and dwarf shrubs expanded, giving them new grazing grounds, but also forcing them into new migratory routes and seasonal rhythms. Forest-dwelling species had a harder time. Animals that depended on closed-canopy woodland, some birds, small mammals, insects, found their habitat shrinking and fragmenting into scattered patches. To survive, they either had to adapt to more open environments, squeeze into the remaining forest refuges, or follow the trees south. Predators responded in turn. Wolves, big cats, and other carnivores that hunted open-country herbivores probably found their ranges shifting with the prey. In some regions, cooler, drier conditions might have favoured pack hunters over ambush predators, reshaping not just who lived where, but how they hunted and interacted. Food webs, the networks of who eats whom, were being rewired. A plant that once grew under a forest canopy might now stand alone on wind-swept ground. Insects that had fed on that plant could lose their shelter, becoming more exposed to frost, heat, or predation. Birds that ate those insects might need to switch diets. Little cascades like this, multiplied across thousands of species, add up to wholesale ecological reorganization. And the stress was not just about movement. For many species, the Younger Dryas meant living close to their physiological limits. Longer winters, shorter growing seasons, more frequent freeze-thaw cycles. Animals with flexible diets, broad tolerances, and wide-ranging habits generally fared better. Specialists, tied to narrow niches, risked local or regional extinction, hidden inside lake sediments. Another signal of ecosystem change shows up as thin, dark layers, charcoal. When organic material burns, it leaves behind microscopic fragments of charcoal that can drift into lakes and settle into the mud. By counting these fragments at different depths, researchers can reconstruct something like a fire history for the surrounding landscape. Across many regions, Younger Dryas deposits carry distinct charcoal patterns. In some places, charcoal increases as the climate turns colder and drier. More open, grassy landscapes with sparse forests tend to burn readily, especially in seasonal climates with dry summers. Lightning strikes or human-set fires can send flames across large areas, leaving behind a signature of frequent, lower-intensity burns. In other areas, especially where conditions became not just colder but also wetter, charcoal may decline. Wet tundra, bogs, and sparsely vegetated glacial forelands are harder to ignite and sustain large fires. Here the cold brought not more burning, but less. These fire regimes' patterns of how often, how big, and how intensely landscapes burn act as indirect climate archives. They integrate temperature, moisture, vegetation type, and even, in some cases, human behavior. They also feed back on the ecosystems themselves. Frequent fire can lock a landscape into a particular state, preventing trees from reclaiming ground and maintaining open grassland or shrubland. Rare fire can allow forests to thicken, accumulating fuels that when they finally do burn can produce dramatic, stand-replacing events. During the Younger Dryas, shifts in climate nudged these feedbacks into new configurations. Some areas likely settled into fire-maintained open vegetation. Others, chilled and damp, slipped into regimes where fire became rare, and slow, mossy communities spread. What is striking, looking at all these records together, is how quickly the living world reacted. The primary physical drivers, the cooling of the North Atlantic, the growth of sea ice, the reorganization of winds and currents, may have taken decades to fully establish. But local vegetation in many places responded on the scale of human lifetimes, sometimes faster. Pollen diagrams often show major transitions compressed into just a few centimeters of sediment, representing decades to a century. That is slow geologically, but alarmingly fast, if you are a tree whose seedlings now fail to survive in the harsher springs, or an animal whose winter range has lost its cover. Ecosystems, unlike ice sheets or deep oceans, can pivot quickly when thresholds are crossed. Once certain temperature or moisture limits are passed, entire plant communities can be replaced within a few generations. Animals, able to move faster than plants, can shift even more rapidly, seeking out new niches or abandoning old ones. The land during the Younger Dryas was therefore not simply colder, it was unsettled. For people and animals living through it, the meaningful difference was not the global average temperature, but whether the valley they knew stayed forested or opened into tundra. Whether a once reliable wetland dried out, turning to sedge meadow, or whether new marshy ground formed at the foot of a retreating glacier. Whether fires became more common, filling the air with smoke some summers, or vanished, leaving landscapes choked with unburned litter. From the perspective of lived experience, the Younger Dryas was a time when familiar patterns broke. Migration routes that had worked for generations could fail if key stopover habitats disappeared. Hunting grounds could become unpredictable as animal herds altered their movements. Plant foods, once abundant, might dwindle or shift to new elevations and aspects. Yet the very speed of these ecological changes also created new opportunities. Freshly exposed soils along glacial margins, cold but nutrient-rich, could host pioneering plants. Lakes formed by meltwater and shifting ice dams offered fish and waterfowl. Tundra expansion brought caribou and other cold-adapted prey into regions they had not visited for thousands of years. For human groups scattered across these changing continents, the Younger Dryas was not just an abstract climate event. It was the reshaping of the stage on which they lived. To understand their story, how they moved, how they adapted, and how some of them may have helped drive further change, we have to follow them onto that stage, into the chill of the Younger Dryas world. If you zoom in from the sweeping view of shifting forests and tundra mosaics, you start to see small clusters of people moving through that unsettled world. These were hunter-gatherers, not farmers yet, not city builders, but not primitive either in any meaningful sense. They were experts at exactly the kind of problem the Younger Dryas presented: how to live when the environment won't sit still. Their basic strategy had three pillars. First, mobility. You don't own fields, you don't invest in long-lived buildings. Your wealth is knowledge of where things are, when they're available, and how to get there without starving on the way. Mobility in the Younger Dryas didn't mean aimless wandering. It meant carefully timed circuits across familiar territories, routes tuned to the seasonal appearance of plant foods, fish runs, bird migrations, and large herbivore movements. When the climate lurched and vegetation zones shifted, those routes had to be renegotiated. Second, diet breadth. In a stable, resource-rich environment, you can afford to specialize. Maybe you focus on salmon runs, or mast stands, or a particular herd animal that passes reliably each year. In a patchy, rapidly changing landscape, specialization is dangerous. So Younger Dryas hunter-gatherers, as far as we can tell from bones, plant remains, and wear marks on tools, leaned into flexibility. They took large game when they could, but they also gathered seeds, tubers, berries, shellfish, fish, and small animals. They cracked bones for marrow, rendered fat, and processed plant foods that required grinding, roasting, or leaching to make them safe. Third, risk management. In a world where a late freeze can kill a harvest of wild seeds, or a sudden shift in snow conditions can send reindeer herds down a different valley, you don't assume tomorrow will look like yesterday. So you build buffers, you cache food in pits or rock shelters. You maintain relationships with neighbouring bands, people you can visit or join if your own territory fails. You share within your group in ways that make sure no one bad hunting day dooms a single family. The archaeological record hints at this in subtle ways. Storage pits dug into lowest banks, repeated use of the same seasonal campsites, patterns of stone and shell moving over long distances that suggest exchanged networks, not just random wandering. These strategies played out differently in different regions. Take Europe. At the end of the last glacial maximum, much of northern Europe had been an open, cold steppe tundra, home to reindeer, wild horse, and bison. As the climate warmed before the Younger Dryas, forests began to return, and with them more diverse ecosystems and more varied hunting and gathering opportunities. Then the cold came back. In many areas, open ground pushed south again. Reindeer and other cold-adapted grazers re-expanded. Human groups who had been gradually adjusting to more wooded landscapes suddenly found themselves back in a harsher, wind-swept world. Some responses seem clear. Sites shift. In some regions, camps move closer to the new edges of advancing tundra, tracking herd movements. Toolkits emphasize projectiles and butchery equipment, suited to mobile big-game hunting, but also include grinding stones and microliths, tiny stone blades that could be used in composite tools for a variety of tasks. It looks less like a collapse and more like a pivot. In the Near East, the story is different. Here, in the millennia just before the Younger Dryas, groups often called Natufians had begun to settle more heavily into certain resource-rich zones, especially areas with wild cereals and good water. Their sites, with stone-built structures and heavy grinding stones, suggest semi-sedentary life, at least in some seasons. They were still hunter-gatherers, but they were pushing the boundaries of how fixed a foraging life could be. Then the climate in many parts of the Levant became cooler and, in some reconstructions, drier. The distribution of wild cereals and other key plants shifted. Some archaeologists see a contraction of those semi-sedentary settlements, an increase in mobility, or a return to more dispersed, flexible strategies. Others argue that in some pockets people doubled down instead, managing stands of wild cereals more intensively, experimenting with early cultivation. Not a straightforward line from climate shock to invention of agriculture, but a complex dance of stress, innovation, and local opportunity. In North America, especially near the southern margin of the great ice sheets, and into the interior, people often associated with what archaeologists call Clovis, and later traditions lived in landscapes jolted by the Younger Dryas cooling. Open plains and parklands, punctuated by lakes and river valleys, hosted mammoth, mastodon, bison, and other large mammals. At least some groups seem to have been highly mobile big-game hunters, capable of crossing large distances and exploiting short-lived opportunities. As the Younger Dryas unfolded, some of those large animals declined or shifted their ranges. New lakes formed, old wetlands dried, and vegetation zones shuffled. Human sites appear in different places with changing combinations of tools. Some assemblages emphasize large fluted points associated with big game hunting. Others show a broader focus with smaller points, scrapers and grinding implements that imply more varied diets and activities. Everywhere you look, there is this pattern. People adjusting their strategies as the environment reconfigures around them. But adjustment is not destiny. It is tempting to draw straight lines from climate graphs to human behaviour. A cold snap causes mobility to increase. A drought causes farming to appear. A resource collapse causes cultural disappearance. Real history is almost never that simple. The Younger Dryas likely increased background stress. Shorter growing seasons, more variable precipitation, and patchier ecosystems would have narrowed some options and opened others. In marginal areas, people might have been forced to move, merge with neighbours, or abandon certain practices. In refuges, valleys with persistent water, coasts buffered by the sea, regions where climate stayed more stable, people may have found pockets of relative security that allowed experimentation and long-term investment. Two groups living in broadly similar climates might make very different choices depending on their existing social networks, traditions, technologies, and sheer chance. One might respond to uncertainty by broadening its diet and increasing mobility. Another might invest in more intensive management of a few reliable resources, even if that means more work and more risk in the short term. This is where the debate around cultural transitions becomes delicate. In the Near East, some researchers have linked the Younger Dryas directly to the origins of agriculture, suggesting that cooling and drying pushed semi-sedentary foragers to begin cultivating cereals to maintain food supplies. Others caution that the picture is more complicated. Not all areas experience the same climate changes. Early cultivation experiments may have started before the Younger Dryas in some zones and continued after in others. Social factors, competition, ritual feasting, status displays could have played major roles in why people chose to plant and tend certain plants rather than simply moving on. In Europe, shifts from one stone tool culture to another during this period used to be framed as abrupt population replacements driven by climate. Now, with more sites and better dating, that story looks messier. Continuity in some technological traditions, gradual blending of styles, and evidence of local innovation suggest that, in many cases, people were modifying their ways of life rather than vanishing and being replaced en masse. In North America, the overlap between the Younger Dryas, changes in big game populations, and transformations in stone tool traditions has sparked long-running arguments. Did climate-driven habitat shifts lead directly to megafaunal declines, which then forced human groups to change their economies? Did overhunting play a decisive role? Were both factors entangled in complex feedbacks? The evidence is rich, but not always straightforward, and interpretations vary. Archaeology, by its nature, is good at showing that something changed. We can see when a type of stone point appears or disappears. We can measure shifting frequencies of animal bones in trash deposits. We can identify when grinding stones become common, or when house structures grow more elaborate, or when burial practices show new patterns. What is much harder is untangling why. Climate records can be lined up with cultural sequences, and sometimes correlations are striking. A cooling event that coincides with settlement shifts, a drought period that overlaps with changes in subsistence. But correlation is not proof of direct causation. People live inside layers of influence: climate, ecology, technology, social norms, belief systems, political tensions, and any or all of these can drive change. In the Younger Dryas world, what archaeology can say with some confidence is that human groups did not face a simple uniform crisis. They navigated a patchwork of local conditions, using flexible strategies honed over tens of thousands of years. Some became more mobile, some less. Some broadened their diets, others specialized in new ways. Some seem to have pulled back into refuges, others pushed into newly available lands at glacial margins or along changing coasts. What archaeology cannot yet say, without overstepping the evidence, is that the Younger Dryas forced a single, inevitable path for human societies. Instead, it seems to have acted like a pressure test. It exposed weak points in certain ways of life, rewarded adaptability, and funneled different groups toward different possibilities. Those possibilities included not just new territories and new technologies, but new relationships with the animals that shared their landscapes. To follow that thread, we have to turn to the other actors on this stage, the great mammals of the late Ice Age, and to a question that has become one of the most contentious in quaternary science. What happened to the megafauna as the Younger Dryas unfolded? And what part, if any, did people play in their fate? When people talk about the end of the Ice Age, they often picture it as a kind of mass curtain fall for giant animals. Mammoths marching off into the snow and vanishing, giant ground sloths keeling over, saber-toothed cats taking their last breath right as the glaciers melt and the climate flips. The reality, as far as we can tell, is slower and more uneven. And the Younger Dryas sits right in the middle of the mess, not neatly at the beginning or the end. If you lay out the extinctions on a map, the first thing you notice is that they don't all happen in one place or at one time. In North America, most of the famous megafauna disappear somewhere between about 13,000 and 11,000 years ago, depending on the species and the region. That range overlaps the Younger Dryas almost perfectly. Mammoths and mastodons, giant ground sloths, American camels and horses, the massive short-faced bear, the big cats and oversized bison, many show their last dated appearances in that window, or just before in the centuries as the climate was warming out of the last glacial maximum, and then jolted back to colder conditions. In South America, the pattern looks a little later in many regions. Giant sloths, glyptodonts with their armoured shells, South American horses, camel-like litoptons, and other large herbivores fade out over roughly the same broad period. But local timings vary, and the signal is more stretched. In Europe, it's different again. Some giants were already gone or much reduced before the Younger Dryas really bites. Straight-tusked elephants and some rhinoceros species had disappeared earlier, during previous climatic swings. Woolly mammoth, woolly rhino, and steppe bison survive deep into the late glacial, but their final declines often lag into or beyond the Younger Dryas, with pockets hanging on in isolated refuges. In Australia, the really large animals, giant kangaroos, the rhinoceros-sized diprotodon, huge flightless birds, seem mostly to have vanished long before the Younger Dryas, tens of thousands of years earlier, in a different climatic and human context altogether. So there isn't a single global extinction moment that lines up cleanly with this 1,200-year cold snap. Instead, there is a patchwork of regional crises and slow dwindlings. Still, in places like North America and parts of northern Eurasia, the overlap between the Younger Dryas and the last days of many megafauna is striking enough that people have been arguing about it for decades. What was pushing those big animals toward the edge? Most researchers now talk about three broad categories of pressure, all operating together, rather than one simple villain. The first is habitat change. Large herbivores, and the predators that depend on them, are extremely sensitive to the structure of vegetation. Whether the landscape is open grassland, patchy parkland, shrubby steppe, or closed forest matters, for what they can eat, how they move, and how they avoid predators. The late glacial period was already a time of rapid change as ice sheets retreated and climates warmed. Forests advanced, wetlands shifted, new lakes appeared behind melting ice, coastlines moved. The Younger Dryas then interrupts that trend, pushing some regions back toward colder, drier, more open conditions, but not in a simple rewind. In many places you get novel mosaics, bits of tundra, patches of scrub, stands of trees arranged in unfamiliar ways. For an animal highly adapted to a particular kind of steppe or parkland, that constantly moving target can be lethal. Calving grounds are disrupted, migration routes are blocked or shifted. Seasonal forage no longer appears where it used to. The second pressure is human hunting. By the time the Younger Dryas begins, people are present in most of the regions where late Ice Age megafauna still thrive. Archaeological sites with butchered mammoth bones, mastodon kills, horse and bison processing areas show that humans were not just passive observers. They were active predators, at least in some contexts highly efficient ones. Whether that predation was enough by itself to wipe out entire species is where the arguments heat up. Some scientists favour a strong overkill component, pointing to the relatively rapid disappearance of many large species soon after humans expand into new continents. Others counter that direct evidence of mass slaughter is rare, and that many megafauna populations were already stressed by environmental shifts before humans arrived in force. The third pressure is ecological cascades. Remove or seriously reduce one big player in an ecosystem, and everything else may start to wobble. If mammoths or other large grazers decline, grasslands may give way to shrubs and trees, changing fire regimes and further altering habitats. If top predators are targeted or lose prey, mesopredators, smaller carnivores may boom, putting new pressures on other species. Disease dynamics can shift in altered communities. Nutrient flows that depended on large animals moving across the landscape can falter. These cascades are hard to see directly in the fossil record, but they are a consistent theme in modern ecology, and many researchers suspect similar feedbacks amplified stress during the late glacial transitions. Now fold in one more complicating layer: time. All of these stories depend on when things happen, often at the resolution of centuries or even decades. But our tools for dating events 12,000 or 13,000 years ago are not perfect clocks. Radiocarbon ages need calibration curves that themselves have wiggles and uncertainties. Bone can be contaminated. Old carbon can be recycled into younger sediments. In some regions there are very few securely dated fossils to work with at all. So you might get a mammoth bone that appears to be 12,900 years old, and a nearby human site dated to 12,800, and a charcoal layer marking an ecological shift at 12,700, all with error bars of a couple of hundred years either way. On a graph, the dots cluster together. In reality, the events might be separated by multiple human lifetimes. That fuzziness matters. If a megafaunal population was already in steep decline for centuries before the Younger Dryas began, then the cold snap might look less like the initial cause and more like a final push, or even just a background condition as a long process played out. If human hunting pressure ramped up slowly as populations grew and technologies changed, it might be hard to distinguish a single moment when people caused an extinction, as opposed to them being one of several chronic stresses that narrowed options until there were none left. This is why many paleontologists now resist sharp, cinematic narratives. Extinction, especially for widespread, long-lived species, is rarely the result of a single bad afternoon. It is more often a drawn-out sequence of shrinking ranges, declining genetic diversity, repeated local disappearances and partial recoveries, until a final tipping point is reached. That tipping point might be a drought, a disease outbreak, a few critical breeding seasons lost to unusual weather, or a new predator pressing just a little harder than the system can absorb. In that kind of story, the Younger Dryas is best seen not as a simple trigger, but as an amplifier. It takes populations already living close to the edge, after millennia of warming, habitat reorganization, and growing human presence, and ratchets up the volatility. Shorter growing seasons in some regions, ice-locked winters, or disrupted plant communities might reduce food reliability just when animals need it most. Human groups also feeling the squeeze might turn more intensely to the remaining large prey. In some areas, species weathered that storm. In others, they did not. From a distance of 12,800 years, it can be tempting to draw straight lines. Climate shock, megafaunal crash, cultural change. Up close, the timeline phrase. Last appearances of bones, last signs of dung fungus in lake sediments, last pollen from open grasslands. All of these fade at slightly different times in different places. What the Younger Dryas seems to have done is sharpen all the trends already in motion. It may have turned slow declines into rapid collapses in some regions, while in others it merely nudged populations that were already doomed, or spared pockets where conditions stayed relatively stable. Instead of a single global catastrophe for the megafauna, we see a mosaic of regional stories, each with its own mix of climate stress, human pressure, and ecological feedbacks. And that mosaic, with its blurred edges and overlapping causes, is part of why the mystery of the Younger Dryas is so hard to untangle. To understand the cold snap itself, we have to distinguish what it started from what it merely intensified, what it explains and what was already underway before the temperature fell. So when people say, why don't we just figure out what caused the Younger Dryas? It can sound, from our modern perspective, almost trivial. We have satellites, supercomputers, radiocarbon labs, climate models. Surely we should be able to rewind the tape 12 or 13,000 years and point to the switch that flipped. The problem is, our tape isn't a high-definition recording. It's more like a stack of old photographs. Many of them smudged, some of them out of order, some faded at the edges. And we are trying to reconstruct an entire movie from those still frames. Every climate story you've heard so far in this series rests on what are called proxy records, ice cores where bubbles of ancient air and layers of dust and snow build up year after year. Lake and ocean sediments where pollen, charcoal, microscopic shells and bits of organic matter settle to the bottom. Tree rings in the few regions where trees have lived long enough and been preserved well enough to reach back into that time. Each of these is powerful, but each has limits. An ice core might capture annual layers in the most recent sections, then blur into thicker bands where a single centimetre of ice could represent decades. A lake mud core might smooth over short, sharp events because mixing by currents, worms and roots stirs the top layers before they lock in. Ocean sediments, falling slowly through deep water, can average centuries into a single slice. Imagine trying to describe a thunderstorm from a weather station that only takes one reading every 20 years. You will see the larger climate trend, wetter or drier, warmer or colder over long periods, but a sudden downpour that lasts an hour might vanish into the noise. Something similar happens with abrupt climate shifts. We know the Younger Dryas was rapid on geological timescales, but was the onset of cooling in a given region a matter of a few years, a decade or 50 years? Did the key changes in ocean circulation happen over a single winter, or did they ramp up over several generations? Our proxies often can't tell us. They smear sharp edges, round off corners, and average over the very windows of time where, for understanding causes, the details matter most. On top of that, different proxies respond to different things. Pollen in a lake core might tell you that spruce forest replaced open grassland over a few centuries. But that switch might reflect temperature, rainfall, snow cover, soil moisture, or some tangled combination of all of them. An oxygen isotope curve in an ice core might show a clear cooling trend, but that same signal can be affected by where the moisture came from, how storms tracked, or how much snow fell each year. We end up with good relative stories. This changed before that, this region cooled while that region warmed, but the exact timing and the exact link between cause and effect remains fuzzy. Then there's the issue of regional asynchrony. The Younger Dryas is named after a flower that flourished again in Europe when things turned cold. The first really clear signs of that shift were in Greenland ice and European lake sediments. But the planet is not a single uniform block of air and water. When the North Atlantic circulation weakens, some places cool sharply, but others might actually warm because storm tracks shift, monsoons reorganize, and heat gets stored differently in the oceans. The southern hemisphere has its own rhythms. The tropics march to their own drums of rainfall and ocean currents. If you line up records from Greenland, North America, Europe, the North Atlantic, the Arabian Sea, tropical South America, New Zealand, Antarctica, you don't get a single neat instant global step. You get a pattern that ripples. Some sites show an abrupt change around 12,900 years ago. Others start to drift a little earlier. Some lag by centuries. Some show almost no obvious Younger Dryas signal at all, or something muted and indirect. Part of that is because the regional climate impacts really were different. Part is because the dating for each core or cave stalagmite or shoreline terrace has its own uncertainties, radiocarbon calibration, layer counting, uranium-thorium ages, all with their own margins of error. If two events are within a couple hundred years of each other, they might be simultaneous, or one might actually precede the other by several human lifetimes. From our vantage point, the dots on the graph might overlap. On the ground, people and ecosystems might have experienced them as separate episodes. This makes it hard to say whether, for example, a pulse of meltwater into the North Atlantic happened first and triggered the cooling, or whether it was part of a larger response that unfolded as the climate system shifted. It makes it hard to pin down whether changes in monsoons, or dust transport, or sea ice were leading or lagging indicators. Another complication is that the Earth system has feedback loops that can make very different triggers look similar once they've run their course. Start with a burst of meltwater from a gigantic glacial lake. Fresh water reduces the density of surface seawater, weakens deep water formation, slows the Atlantic overturning circulation. The northern Atlantic cools. Sea ice expands. The white ice reflects more sunlight, amplifying the cooling. Colder oceans take up more carbon dioxide from the atmosphere, slowly reinforcing the trend. Now imagine instead that the initial nudge came from a volcanic cluster, or a modest change in solar output, or a shift in atmospheric circulation. The path might look different at first, but once temperatures in the North Atlantic drop far enough, similar feedbacks can kick in. Sea ice growth, snow cover, changes in wind patterns, rearranged rainfall. After a few decades or centuries, you can end up with two climate histories that look remarkably alike in the proxies we measure, even though their first domino was different. And then, as we saw with megafauna and people, the ecological and human responses layer on top of the physical changes, adding more feedbacks, vegetation, shifts that alter dust and carbon, fire regimes that change soot in the atmosphere, shoreline migrations that reshape local climates. When scientists look back from thousands of years away, they see the integrated signature of all of that. Untangling which wiggle in which curve is the mark of the trigger, and which are the marks of the system reacting, is not obvious. On the human side of the mystery, there are also the quieter forces that shape science itself. Some ideas catch fire quickly. Exotic explanations, a comet impact, a sudden global wildfire storm, a single catastrophic flood, unnaturally compelling. They produce sharp cinematic narratives. They make for memorable diagrams and headlines. Other explanations are more mundane. Gradual ice sheet retreat, changing drainage pathways step by step. Modest but persistent changes in wind and ocean patterns. Complex combinations of meltwater, sea ice, and internal variability. When a dramatic hypothesis is proposed, it tends to generate a burst of papers testing it, exploring it, criticizing it. Some positive results are more likely to get published than null results. Negative or ambiguous findings can sit in file drawers or appear in smaller journals that fewer people read. Over time, this can create the illusion of stronger support than actually exists, at least until replication studies and larger syntheses are done. Meanwhile, the records themselves are being steadily refined. A lake that was dated 40 years ago with a handful of radiocarbon samples might be revisited with dozens of high-precision dates and new methods for detecting contamination. An ice core that once had layers counted by hand might be reanalyzed with laser instruments that pick up annual markers missed before. Sometimes these revisions move events by a few hundred years one way or another, enough to change the story about what caused what. This is why debates about the Younger Dryas have lasted decades and will probably continue. It isn't that scientists enjoy arguing for its own sake. It's that the data are right on the edge of what our tools can interpret clearly, and small shifts in interpretation can have big consequences for which narrative seems more plausible. In responsible Earth history, this uncertainty isn't brushed away. It's part of the story. When you see date ranges instead of single years, when a paper says approximately or within error of or broadly synchronous, that's not hedging for the sake of it. It is a sign that the authors are respecting the limits of their proxies and methods. Researchers will often present multiple scenarios. If the meltwater pulse preceded the cooling, then this mechanism is favoured. If they were simultaneous within error, then this other mechanism looks better. They use ensembles of climate models, each with slightly different assumptions, to see which combinations of triggers and feedbacks can reproduce the patterns seen in the ground. Instead of one neat answer, you get a family of plausible stories, ranked by how well they fit the evidence we have, and by how well they survive new tests as more cores are drilled, more caves sampled, more dates cross-checked. From a distance that might sound unsatisfying, but in another sense, it's comforting. The Younger Dryas reminds us that the Earth system is both understandable and irreducibly complex. We can sketch the outlines of what happened with increasing confidence, but the fine-grained details, the exact storm tracks, the exact winters when rivers first froze solid, the exact conversations people had under unfamiliar skies, will always be a little blurred. In that blur, there is room for humility. And out of that humility, out of those careful error bars and cautious phrases, a clearer picture slowly emerges of what the best explanations look like today. If you gathered all those families of stories into one room and asked them to introduce themselves, one pattern would stand out almost immediately. Almost everyone, no matter which camp they belong to, ends up talking about water and the Atlantic. In the most widely used reconstructions, the Younger Dryas begins with a simple ingredient, a lot of fresh meltwater arriving in the wrong place at the wrong time. As the great North American ice sheets retreated, they left behind vast lakes dammed by ice and moraines. Lake Agassiz, Lake Ojibwe, and others like them were not lakes in the way we usually imagine. They were inland seas, holding more water than all the Great Lakes combined. Most scenarios picture a moment when those lakes found a new outlet. Maybe it was an ice dam that failed catastrophically, suddenly connecting a lake to the North Atlantic or to the Arctic Ocean. Maybe it was a more gradual routing change, as the weight of the ice sheets lessened and the land beneath them rose, tilting watersheds just enough for flow to spill toward a different coast. Either way, a large enough flood of fresh water into the North Atlantic would have done something very specific. It would have lightened the surface waters, the Atlantic's great overturning circulation, the conveyor that pulls warm, salty water northward and sends cold, dense water back into the deep, runs on differences in temperature and salinity. Fresh water dilutes the salt, making it harder for surface water to sink. If you add enough at the right latitude, you can slow or even stall parts of that conveyor belt, slow the overturning, and the downstream effects ripple through the system. Less warm water reaches the high northern latitudes. The North Atlantic cools, sea ice expands, winter winds sweep across larger ice fields. Storm tracks shift. Heat that would have been vented to the air in the north instead piles up elsewhere, deep in the ocean or in other basins. In this picture, the Younger Dryas is what happens when the Atlantic's engine chokes on a freshwater surge. Greenland cools abruptly because it sits in the heart of that circulation pattern. Europe chills as sea ice pushes south and winds reorganize. Parts of the tropics change because the big overturning cell that links the hemispheres is altered. Rain belts move, monsoons weaken or strengthen in different regions. Many climate model experiments support some version of this chain of events. When researchers pour fresh water into the virtual North Atlantic in their simulations, they can often reproduce at least the broad outlines of a Younger Dryas-like pattern. Sharp cooling around the North Atlantic, mixed signals in the tropics, more modest or even opposite changes in the far south. Other lines of evidence point in the same direction. Sediment cores from the North Atlantic show layers rich in ice-rafted debris, pebbles dropped by melting icebergs, around the onset of the Younger Dryas, hinting at expanded sea ice and glacier carving. Some marine records show shifts in the kinds of tiny plankton that like cold, fresh surface water, replacing those that prefer warmer, saltier conditions. To many researchers, this has the feeling of a central spine to the story. But around that spine, other ideas cluster, not as rivals so much as supporting actors, possible co-conspirators. Impact proponents argue that a fragmented comet or asteroid striking an ice sheet could have been the trigger that destabilized those giant lakes, or that lofted dust and soot into the atmosphere, darkening snow and increasing melt. Volcanologists point to episodes of heightened volcanic activity that might have cooled the atmosphere directly or altered wind patterns, setting the stage for an ocean response. Some atmospheric scientists emphasize internal variability, the way wind belts, pressure systems and storm tracks can shift into different semi-stable modes even without an obvious external push. In their view, the meltwater was important, but the precise timing and regional pattern of the Younger Dryas may also reflect the atmosphere's own chaotic tendencies. There are proposals about sea ice as an active player, not just a passive response. In these, subtle changes in winds produce a rapid expansion of sea ice, which then feeds back into the ocean circulation beneath it. Others highlight vegetation and dust, how changing land cover on the newly deglaciated continents altered how much sunlight the surface absorbed or how much iron-rich dust fertilized distant oceans, subtly changing carbon dioxide and climate. In the more measured versions of these debates, the question is less, which mechanism is right, and more, how much did each one matter and when? Did a meltwater pulse get things started, with volcanoes, sea ice and vegetation feedbacks amplifying the shift? Did an internal atmospheric reorganization push the ocean toward a threshold that the next big lake outburst happened to shove it across? Was there perhaps no single dramatic trigger at all? Just a series of smaller nudges that, in combination, tipped a delicately balanced system? What would it take to move these from plausible sketches into something closer to consensus? More than anything, cleaner timelines. If we could pin down within a few decades, rather than a few centuries, exactly when key meltwater routes changed, exactly when North Atlantic deep water formation weakened, exactly when sea ice jumped southward, then many of the branching storylines would either align neatly or fall apart. That means better dates on the ancient shorelines of glacial lakes to see precisely when they drained and where the water went. It means new high-resolution cores from critical choke points in the ocean, the Labrador Sea, the Nordic seas, the gateways where deep water forms and spills. It means ice cores and cave deposits with tighter age models, so that a volcanic ash layer or a sudden dust spike can be matched confidently to an ocean or lake signal far away. It also means models that can handle more of the messy details. Current climate models are powerful, but most still smear out key processes. Icebergs, narrow currents, small-scale mixing, over grid cells that can be dozens of kilometers wide. As computing power grows, models that can resolve more of this fine structure and can be tested against more detailed proxies may help distinguish between triggers that look similar at coarse scales but different in the details. Beneath all of this is a deeper reason the Younger Dryas keeps drawing attention. It is not just an archaeological curiosity, a strange cold snap tacked onto the end of the last ice age. It is one of the clearest examples we have that the climate system is capable of crossing thresholds. For a long time, people imagined climate as something that drifted gently, like a thermostat you nudge 1 degree at a time. The Younger Dryas is evidence that, under the right conditions, a system can hover near a tipping point and then, with a relatively small push, reorganize abruptly, locking in a new pattern of winds, currents, ice and rainfall that persists for centuries. Today, when scientists warn about the potential weakening of the modern Atlantic overturning circulation under continued greenhouse gas emissions, the Younger Dryas is there in the background. Not as a perfect analogue, the world was configured very differently then, with huge ice sheets and different coastlines, but as a proof of concept that this mechanism is real and that it can produce large, rapid changes. Understanding exactly how that ancient event unfolded is one of the ways we probe where our own thresholds might lie. How much fresh water from Greenland would it take to matter? How fast could circulations change? Which regions would feel it first, and which would be buffered for a time? Where do feedbacks amplify a small change into something much larger? We will probably never have a single crisp frame of the night the world flipped into the Younger Dryas. But as the lines of evidence converge, meltwater routes, ocean cores, ice and dust and pollen layers, a picture sharpens of a climate machine that is both delicate and resilient, prone to long periods of stability punctuated by sudden shifts. Listening to that ancient story told in bubbles of air and grains of mud is one way of listening to our own future. And just as the Younger Dryas began abruptly, it also, in its own time, came to an end. The way it ended may be the most quietly astonishing part. After more than 1,000 years of cold, the Younger Dryas did not fade gently like winter easing into spring. In many records it seems to stop almost as abruptly as it began. In the Greenland ice, the shift looks like a stair-step. Ratios of oxygen isotopes, which track temperature, climb in just a few years. Dust levels drop. Snowfall increases. Chemical markers that had screamed cold and dry for centuries suddenly whisper, warmer, wetter, more like the world we know. Lake sediments across Europe and North America tell a similar story. Pollen from tundra shrubs and cold-loving grasses dwindles. Trees move in birch, pine, oak, marching north and uphill in what, on human timescales, feels like fast motion. In some places, the transition from Younger Dryas vegetation to early Holocene forest happens within a human lifetime or two. Ocean cores show changes as well. Species of tiny plankton that prefer colder surface waters decline. Those that like warmer, saltier conditions return. Proxies for deep water formation in the North Atlantic strengthen again, hinting that the great overturning conveyor, whatever had throttled it, was spinning back up. Exactly why it happened when it did is still debated. Maybe the big glacial lakes had finally emptied or rerouted, ending the pulses of fresh water that had been weakening the Atlantic engine. Maybe the ice sheets had retreated far enough that their influence on winds and sea ice was no longer dominant. Maybe slow internal rhythms in the ocean atmosphere system, the same ones that can nudge us into and out of modes like El Niño today, simply carried the system back across a threshold. What seems clearest is that the climate system did not have to climb back out one cautious step at a time. Once the balance of heat, salt and wind crossed whatever tipping point had held the Younger Dryas in place, feedbacks reversed. Sea ice shrank, exposing darker ocean that absorbed more sunlight. Snow lines retreated, lowering the planet's reflectivity. Vegetation changed, altering how water cycled between land and sky. The same web of interactions that had locked the world into a cold pattern for centuries now helped it settle into a warmer, more stable Holocene state. The tempo of that shift is a reminder. On geological timelines, a few decades is an instant. Yet in that instant, storm tracks moved, monsoons reorganized, ecosystems migrated, and human cultures living through the change would have watched their familiar seasonal patterns slide into something new. When people say nobody knows why the Younger Dryas happened, that sharpness is often what they are responding to. The feeling that something so big should not be able to pivot so fast. But the real state of the science is subtler. We are not staring into a complete void. We have strong candidates for many of the pieces: freshwater and the Atlantic overturning, sea ice and winds, vegetation and dust, internal variability. The uncertainties live in the links between them. Which trigger mattered most, how they lined up in time, how sensitive the system really was to each shove. Those open links are not a failure. They are an invitation. In the coming years, new ice cores will be drilled from untouched parts of Greenland and Antarctica. Sediment cores will be pulled from seafloor ridges that have never been sampled. Ancient shorelines of long-vanished lakes will be mapped with better tools. Models will grow sharper, able to represent icebergs and narrow currents and turbulent mixing that older generations could only smear out. As those pieces arrive, there are a few things to listen for. Signs that the timing is tightening, meltwater pulses, ocean changes, volcanic layers, and dust spikes lining up with fewer and fewer centuries of wiggle room. Evidence that some proposed triggers lack the right dates or magnitudes and quietly fall away. Clues that others, perhaps a particular routing of fresh water or a specific pattern of sea ice expansion, keep showing up in independent lines of data. You may also hear more about other abrupt events in Earth's past. Earlier cold snaps and warmings, smaller cousins of the Younger Dryas, scattered through the Ice Age record. Comparing those will help us see which mechanisms are unique to one moment and which are part of a larger pattern of how the climate machine behaves near its thresholds. Beneath all the technical detail, the broader lesson is steadying. The Younger Dryas shows that climate can jump. It also shows that those jumps have causes, and that with enough patience, enough cause and dates, and careful models, patterns emerge from what once looked like noise. As you drift towards sleep, you can imagine future researchers reading layers of ice and mud we have not yet touched, teasing out the last missing links in this 12,800-year-old mystery. Not to erase the wonder, but to understand a little better the planet that carries us. If you've enjoyed wandering through this piece of Earth's deep history, you can help others find it too. Gently tap like, subscribe if you'd like more calm journeys through the past, and let us know in the comments where in the world you're listening from tonight.